So let's talk now about multi-commodity flow. So far, everything we've looked at has been a single commodity, and that is there's only one product that flows from our sources to our sinks, our origins to our destinations. And it doesn't matter where my product came from, which of the origins or which of the destinations it goes to, it was the same one. So now we're going to introduce a more realistic assumption that there are multiple commodities, or the multi-commodity flow problem. There's more than one product, and so each region might demand a certain quantity of different types of products, and that means they have to come from different locations, and you have to treat them differently. This is much more realistic. However, in a lot of cases, we still solve the single commodity problem. Why do we do it? Well, it's easier. It's much simpler than the multiple commodity one. It's smaller, and sometimes it's perfectly appropriate. When's it appropriate? It's appropriate if there's no bundling between the different commodities or shared constraints. So if I can isolate the two supply chains and they don't interact at all, do them as single commodity flow. There's no reason to complicate the mix. For example, if I'm flowing bananas and cantaloupes and they can't go in the same facilities or use the same transportation modes, treat them as separate models. Treat them separately, model them separately. However, if there are interdependencies, if, for example, both products, both commodities go through the same distribution center, or they're manufactured at a plant that has a common capacity constraint, then the effect of one will impact the other. So if I produce more bananas in that case, it might lower the capacity available for cantaloupes. So then there's interaction. Then we have to model it as a multi-commodity flow problem. But if that doesn't happen, treat them as independent single commodity problems, solve them quickly, easy to go. But the primary difference between the single commodity and the multi-commodity problems is that the formulation gets bigger and a little more complicated. So let's look at the formulations. Here is the single commodity flow formulation you should be very comfortable with. I've got my objective function that I'm minimizing for all my costs for moving a product from I to J. So I have just variable costs here. There's no fixed costs in this model yet. We could add them in, but we're not going to. We're going to keep it simple here. And then I've got a series of constraints. I've got my supply constraints or my capacity constraints at origins. I've got my demand constraints that I've got to meet at each of the destinations. I've got my conservation of flow constraints to make sure if product comes into a transshipment point, the same amount goes out. Product doesn't magically arrive or magically disappear. And then I've got this capacity, and this is also at the transshipment points. You could actually put this anywhere, that the amount of product flowing at a certain facility can't exceed a certain capacity. Okay, so how would I make this, or how would this look differently in multi-commodity flow? Well, it doesn't look that different, actually. There's one big difference that you'll notice is we introduce a new indice, K, so there are K different products, and so I have everything subscripted. So now instead of Xij, the flow from a product from I to J, it's Xijk. And so it's the flow of product K from node I to node J. So it's a little more specific. The costs can also be specific by product. They don't have to be. And if they're not, I just get rid of the subscript K. If it costs the same amount, regardless of the product, for a certain transportation link, then I don't need to have a separate cost. But I have the same sets of constraints. I've got supply constraints. I've got demand constraints. I've got conservation of flow constraints. And then I've got the capacity constraint. Now, the only one I want to talk about for just a second is for the supply constraints. So I've got this top one is limiting it by each commodity. I can only produce, or I can only source so much of each commodity at each origin I. The second one is saying, regardless of the commodity, I can only produce a certain total amount. So let's say I have two commodities, and each one I can produce 100 units of each. But my total system or capacity at that facility is only 150. So while I could produce 100 of one, if I do that, then I can only produce 50 of two. Or if I produce 100 of two, I can only produce 50 of product one. So you can have different hierarchy or layers of capacity, which is very realistic. So it helps me with the allocation of different products that I will produce. Let me just clean this up a little bit. All right, so this is the formulation. So the question is, how do we solve it? What is this going to look like? So let's do an example. And this is the Worldwide Universal Widgets Unlimited, or WUWU problem. As we all know, WUWU is a global manufacturer of widgets. They have 3 plants in Chicago, Dallas, and Miami. And they send product through 2 distribution centers, one in Atlanta and one in Boston. And then they send them on to 3 different state regions for demand: New York, Pennsylvania, and Virginia. And so the product always flows from plant to distribution center and distribution center to region. There's no bypassing in this model. So this looks very normal. This is a straight transshipment problem. You can do this in your sleep, right? But what makes it complicated is this. Each of the plants manufactures 3 different versions of the widgets that we call versions 1, 2, and 3. And each of the regions in the demand, they will demand different quantities of each of these. So you can see that this makes it a little more complicated, thus multi-commodity flow. Okay, the question that we want to answer here is where and in what quantity should WUWU manufacture each product and distribute it to meet the demand in each of the regions at the lowest cost. So it's the same objective function, really, as we had for the transshipment model. We need a lot more data. So each plant is capable of manufacturing all the products. They have different capacity levels and different costs. The costs for transportation differ by lane as well as by product, and the demand differs. So what I have here in the top left chart is for each of the products, product 1, product 2, product 3, the cost of transportation. So for example, if I manufacture in Chicago and ship through Atlanta and then go on to Pennsylvania, the cost of each unit would be 6 plus 6, $12 per unit. If I manufacture in Chicago and go through the Boston distribution for product 1 and then on to Pennsylvania, then the cost would be 5 plus 6, or $11 per unit. So you can see how I set this up. It's just giving all the different costs, and they can be different by commodity, by lane, so you can make it anything you want. Then I've got capacity at each of the distribution centers. Atlanta's 200, Boston's 500. I've got capacity at the plant, and you can see it's by product except for Dallas. Dallas has individual plant product capacities for each of the different products, but then it has an overall plant. So while I can do up to 125 units of product 1, up to 200 units of product 2, and up to 150 units of product 3, combined, it can only be 250. Now, if this capacity for Dallas as a whole was greater than the sum of the individual capacities, then it doesn't matter. It's useless. Why have it there? It's not binding. But if it's less than the sum of the individual ones, then it could have an effect. And finally, I've got regional demands for each of the regions, each of the products, and you can see they vary. In Virginia, they like product 1. New York favors product 2. And Pennsylvania favors product 3. Realistic, that different regions will have different preferences and appetites for different products. So how do I solve it? Well, I do the same formulation. This is in a spreadsheet. This is in Excel. And this should look very similar to the transshipment problem, just bigger. And so let's go through this. I've got my objective function up here in cell B4. And then I've got all my decision variables that I keep in yellow. They're in row 9. And right beneath that is the individual cost. And so the XIJs and the CIJs, IJKs are there. And cell B4 is just the sum product of my decision variables and their respective costs. Same thing as it's been for every model we've done. Then I'm going to have a series of constraints, and every one of the constraints has the left-hand side, and each of these left-hand sides is just, again, a sum product of the decision variables that are in row 9 multiplied by each respective row. In this case, in cell, AM13, it's going to be the decision variables, right, multiplied by whatever's in this row, row 13. All right, which is just what's coming out of Chicago. And you see it's capturing the supply constraints for Chicago. So this is identical to what we've done a half a dozen times so far. And you have the right-hand side. This is the input data that you have. So the constraints, I've got my capacity constraints at each plant. I've got my demand constraints at each customer region. And I've got my DC capacity. And then I've got my conservation of flow at each DC. Boom, we know how to solve this. So it looks complicated, it looks big, it is big, it gets big as soon as I introduce commodities, multiple commodities, but it's the same model as the transshipment model. It just has a couple little tweaks, but I still have essentially two formulas. A sum product up here for the objective function and sum products here. That's it. It's so easy. Okay, so what's the solution? We know how to do this. I have my objective function. I put in my changing variables or my decision variables. I've entered in my constraints. I make sure it's simplex. Make sure their unconstrained variables are non-negative. And then I solve it. And you should get a solution of $6,525. And I've got my decision down here, or the solution down here. And so it's saying I'm going to ship product 1, manufactured in Chicago, and ship 125 units to Boston. Then I'm going to make 100 units of product 1 in Dallas and ship it to Atlanta, and so forth. You have all the different numbers. Now, it's very complicated, and so what we're going to do next, in the next segment, is analyze these results, because we want to look at it a little more in depth than just what's showing up in the individual decision variables.